Um, and then tomorrow we're doing day 2. So it'll be recursion through for Monday, and then this is pretty much the last thing we'll cover in the curriculum.
Oh, there's no class tomorrow, is there?
Oh, sorry, I'm going to say Monday, or
Okay.
like the next class.
Okay.
Yeah. Yeah. So recursion is one of those things that it feels pretty intimidating, and I think people maybe overestimate kind of how important it is in the actual full stack process, full stack
That's
admissions process.
actually the last topic uh, I got to on my own, and yeah, after during this point, learning recursion is when I decided I have to take some classes.
Okay. Well, hopefully we can make it a lot clearer for you then. Um, yeah. So let's just get right to it, right? So the simple answer for what recursion is recursion occurs when a function calls itself, right? It's not the most helpful thing to kind of recite intellectually. It's much easier to see it in action and try to understand kind of the logic behind what it's doing. Recursion, in the way that we're doing it today, one of the traps that kind of people fall into at this point is everything we do with recursion today can be done with a loop, right? As in, with any given function, if I say, hey, write this 5 times, you could do a loop. You could do a loop that you do a normal for loop that goes from 1 through 5 and the counter. You can also use a recursive loop too. And recursion by definition is pretty tricky and pretty difficult. And so most folks try to say, well, let me do it the simpler way, and that works. Except in the next lesson, we'll kind of show you some categories of problems that can only be solved with recursion. And so, for both today and also the next lesson, we are very well aware that you could do these problems without recursion, at least for today. But still try to use recursion because the concepts that you learned today is going to carry over into the next class, where using a traditional loop will not work anymore. Okay, so yeah, so recursion. So the reason why people usually use recursion is because recursion, by kind of what it's really kind of good at, or one of its core strength, in addition to doing something over and over again, is that it really breaks the problem down into the smallest piece possible. Normally, when you see a recursive function, the idea is not like let's do this really long complex thing. It's just say, hey, let's do this actually pretty simple thing, but let's do it over and over and over again. And usually speaking, recursion is best when you're doing problems for which you don't actually know beforehand how many times you intend to do it. Right? If I know beforehand I want to do this 10 times, then I would just use a for loop. If on the other hand, for example, one category of problems is say, hey, what if I have an array of things, and the things in there could also be arrays, and I don't know how deep those layers of nesting goes, right? How do I get to the very innermost layer of the array? That's a question in which, when we start the problem, you have no idea how deep the deepest layer in the array element is. But recursion can kind of help you get to the bottom of it as fast as possible. Um, so yeah, so recursion is very powerful, and you see it in a lot of kind of higher level applications, especially related to AI and machine learning. So let's take a look at kind of what it looks like in real life here. Um, One of the precursors to understanding how recursion works is to understand how the call stack works. JavaScript is single threaded, and that just means something that you've already seen in practice, which is pretty much that if I have 10 commands in JavaScript, and I start at line one will not run, or like line two will not run until line one finishes, right? Similarly, line three will not run until line two finishes, and so on and so forth. That's why when I have a bunch of console log statements in a row, I can tell you with complete accuracy the order in which those statements are going to print out, because JavaScript is single threaded. It's like a one lane road, right? The cars have to be in a certain order. There's no room to pass. There's no way to leapfrog one another. And so the call stack, essentially, if we keep going with the analogy of the road, it's basically the order in which these cars are, right? And you can think of each car as a separate command in JavaScript. The most common way that people think about kind of visually the call stack is, if you've ever been in a buffet line. If you remember, they'll have a stack of plates at the beginning of the line, right? And that's usually the visual image I think describes a call stack fairly well. Each command or each thing that you do in JavaScript, it's like a plate, right? And so if you remember how a buffet plate works is that if I have, let's say, a pile of 10 plates on this at the buffet line at the beginning, and someone brings over an extra plate, well, what do? I put that 10 plate, sorry, I put that new single plate on top of the 10 existing plates, right? Similarly, if I wanted to get a new plate to get some food, I would take the topmost plate off of that stack. And so this is what in computer science what they call a last in first out kind of I guess ordering or sequence, in that the last thing that gets put in is the first thing that comes out, right? The opposite of this, for example, would be something called FIFO, or first in first out, right? So if I was in line to buy a ticket, the person who's been in line the longest gets the next ticket, right? That's how, usually when you wait for something in a line, that's how it works. In a call stack, it's the last thing that came in. That's the first thing that gets removed, right? So going back to the buffet analogy, if I have a stack of 10 plates, someone puts another plate on top of that stack. Well, the next person that comes by and tries to grab a plate, they're not going to grab a plate from the very bottom of the stack, right? They're going to grab the one that's at the very top. And so that's and so what that means in the sense of JavaScript context is just that when a computer is running these commands, if a bunch of commands pop up, it will always start working on the latest command that was added to the call stack. Okay, and so once it finishes that command, then it will go to the next most recent command that's added to the call stack, and so on and so forth until it resolves all the plates or all the JavaScript commands in the call stack. So let's take a look at what that works, because I know that like verbally that may not have been as clear. So here, if I have a function first, which is console logs that I am first, I have a function second that console logs that I am second. Well, if I just print these out, as JavaScript goes through these lines of code, right? It gets to line 5 and line 7. It recognizes that, hey, there is a function, but nothing is being called, right? And so nothing is being added to the call stack. We then go through lines 8, 9, 10, 11. It sees that there's another function, but once again, nothing is being called, and so nothing is added to the call stack, right? The call stack, by definition, means we only add something to it whenever we call a function. On line 13 is the first instance in which we actually call a function, right? We call it the first function, and so that means we add first to our call stack. And now, because this is the first thing that's added, JavaScript now says, okay, before I move past line 13, I have to resolve whatever is on line 13, which means I need to resolve this first function. So then it takes the most recent plate on the call stack, which in this case is the first function, and it resolves it. It console logs out first. Okay. Once it does this, it says, hey, I'm now done with the first function. I finished resolving it. I then remove it off my call stack, right? It's like, you can think of the call stack as almost a to-do list. Like when I have something to do, I put it on there. Once I'm done with it, I take it off, or I cross it off. And only once am I done with that first function do I move on to line 14, which then says, hey, here's another function for you to process, the second function. So then I go to the second function, I invoke that, I print out second, and then once that function is finished printing out, I then remove it off my call stack, and then my call stack is going to be empty. Make sense so far? Yep. So let's take a look at a function that does something maybe a little bit more than once, right? So here I have a function called countdown, and all it does is it takes in a number, and then I create a for loop on line 4 there that starts at the number. Every single iteration of it takes and it makes decrements a number by 1, and I stop when the number is greater than is greater than or equal to, or sorry, I stop when the number is no longer greater than or equal to 1, right? Basically, once it hits 0, I stop. And for every instance, all I do is I console log out the number. And so if I call countdown of 5, what that does is that's going to iterate through, and it's going to print out 5, 4, 3, 2, 1, and then the for loop is going to stop, and the function is going to finish. Nope. Sorry. Oh, sorry, this is, I think, a duplicate slide. Okay. Now let's look at another example in which there's more than kind of one function call at a time. And so because everything we've seen so far is almost like I add a function to a call stack, I resolve it, I move on to the next function, right? So our call stack never gets more than one function deep, right? There's never more than one thing on our to-do list. But in recursion, there's very often multiple things on our to-do list. So let's see how that happens. Here I have a function called first. I define it. When I call it, what it does is it console logs out I am first. It then invokes this second function, and then it console logs out first is finished. And then I have my second function, which is console logs out I am second. Okay, so if I was to run this code on my call stack, well, everything between lines 1 through 10 is just defining the functions, right? I don't actually call anything. So there's nothing on my call stack until I reach line 11. When I get to line 11, what happens? Well, I'm now invoking the function first, so that goes onto my call stack. And so let's take a look at what happens, right? If I try to actually kind of invoke or walk through the first function, I go to line 1, I go to line 2, which console logs out I am first, and I see that. And then on line 3, what happens next? Well, on line 3, it says you need to invoke the second function. And so here at this point, notice how I now add the second function onto my call stack, right? I don't take the first function off because I haven't finished with the first function yet, right? And so JavaScript, so it's kind of conceptually, it's like I'm not going to take something off my to-do list if I haven't finished it yet. But what this sequencing on the call stack is telling me is that in order to finish the first function, I need to finish invoking the second function. Sorry, did you have a question there?
I'm thinking.
Yep.
The first function was I am first.
Yep.
It printed it, so it console logged it. So to me, it completed it. Why does it need to call this? Why does it need to finish calling the second function in order to consider first? Oh, because first is not done yet because it has another function to call.
Okay. The first function, it covers lines 1 through 5, right? So all we've done is we've finished line 2. We haven't finished lines 3 and 4 yet.
Right.
JavaScript doesn't quite know what lines 3 and 4 are yet. It just knows I haven't gotten there yet. So therefore, I can't have finished the function. And so when it gets to line 3, now what JavaScript says is, hey, look, here's another function call. Let me add to my call stack. I can't move on to line 4 until I finish line 3, right? So I need to do whatever line 3 is telling me to do right now. And line 3 is telling me to invoke a function. So therefore, let me add it to my call stack. And let's finish resolving the second function. And so now, at this point in time, JavaScript says, I want to finish the first function, but in order to do so, it's making me invoke the second function. So I need to finish calling the second function. So how do I call the second function? I go to line 7. I go to line 8. I actually invoke it, which console logs out I am second. And now I'm done invoking the second function. Right?
Oh, wait, one sec. Yes, gotcha.
Yep. And so now the second function is done because I've console logged out I am second on line 8 into the screen in the top right-hand corner. I've now reached line 9, so my second function is over. And now once I finish the second function, I can take it off my call stack. Okay? So then JavaScript says, okay, great, I finished this detour on my to-do list. Where did I leave off? Oh, I left off on line 4, right? Because all the time I was working on line 3. I just finished line 3. So then you pick up on where I left off on line 4. And on line 4, I console log out first is finished. And then and only then am I done with the first function. And I can take that off my call stack.
What would happen if function second was above function first?
You mean like when I define it on the page?
Yeah.
Both functions will be hoisted to the top of the page, and so it wouldn't matter. Yeah. 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 I guess one analogy is like, let's say like I wanted to make like a pasta dish, right? Like and I get home, I put the water in the pan, I boil the water, and I realize I have no pasta. Well, then I need to kind of run to the store and get pasta. When I come back, I don't need to start the whole process over again. I just need to put the pasta in the water and pick up where I left off, right? It's very much like this, like the same idea here. I'm trying to do this first function, which requires me to take almost a detour and do the second function. Once I do it, then I can come back and finish the first function where I left it off. So once again, the call stack is just a to-do list, and the most important thing to remember, once again, hopefully you kind of see why we do it, why it does it this way, the last thing that gets put on the stack, so the thing that's on the topmost of the stack, is the one that's currently being worked on. So now let's go back to our previous example of a countdown function where we count down from 5 to 1. But now, rather than doing it through a traditional for loop, let's see how it will look if we were to do it through a recursive function. Okay. So now all I have is this function called countdown. I give it a number, and all it does is it prints out that number. And this is actually another way to do the same problem, right? It's very laborious, but it gets the job done. And the reason why we're kind of doing this extra step and showing how to do it this way is because if you notice now, on lines 4 through 6, the function is actually very simple, right? All it's doing is taking a number and printing it out. The function is the same every single time. The only thing that changes now is every time we run this function, we're passing a different number as the argument. And so this kind of starts off. Sorry, John, take a second to look at that still.
So countdown 5 will console.log
5.
5. Oh, okay, got it. I thought you were doing a countdown, but you're just console logging a new number each time.
Yep, I am, right? And it feels kind of silly, but the reason why we do it this way is because now the idea is that, sorry, let me just go back really quickly. The idea here is that every time we call countdown, we're just decreasing the argument, the number that we pass in by 1, right? That's the only thing that's changing. And so the question now becomes, well, now every time we call it, we're subtracting 1 from the number. Why don't we just have countdown call itself, and it can do that thing where every time it calls itself, it subtracts a number by 1 on our behalf. So rather than me having to write it out, console countdown 5, countdown 4, countdown 3, so on and so forth, it'll just do it for me. And so now I have this countdown function that takes in a number, and it still prints out the number, but then what does it do? It then calls countdown num minus 1. Okay, so let's see what happens now when I call countdown 5. If I go back to my analogy of a call stack, right? I go through lines 1 through 11, nothing happens. On line 12 is the first time I actually call a function. Now on line 12, I call countdown 5. Okay, great. So now JavaScript says, great, let's go to line 8 now. What happens? Well, the first thing we do is we console.log on num, so I print out 5. And then before I finish countdown 5, I need to finish line 9, which says, hey, could you call countdown of 5 minus 1 or countdown of 4 for me, right? Notice how I'm not done with countdown of 5 yet, right? Because to finish countdown of 5, I need to finish line 9 in the code. But line 9 in the code is saying call another function. So then I add countdown of 4 to my call stack. And now I'm calling countdown 4, which once again takes me to line 8, and I'm console logging out 4. After I finish that, the next line 9 says, hey, call countdown and pass in num, which is 4 minus 1, which is countdown of 3. And so if you notice kind of the pattern that's shaping up here, is that like I haven't finished countdown of 5 just yet, because that's the first one on my call stack. And the reason why is because in order to finish that, I need to finish calling countdown of 4. But I can't finish countdown of 4 until I finish calling countdown of 3. And then obviously if I keep going on, countdown 2, countdown 1, countdown 0, countdown -1, and so on and so forth, I've essentially reached this function that is doing what I wanted to do, except it never stops. It just kind of keeps going, right? Countdown of 5 all the way to countdown 1 is great. It's exactly what I want, but I don't want it to go past to 0, -1, -2, -infinity, and so on and so forth. And so this is what we call in JavaScript, when you use recursion and this doesn't stop, this eventually is going to trigger an error in the computer. It's going to say, hey, like the computer is going to try to run this several thousand times, and it will say you've exceeded the call stack size, which basically says that, hey, you've had this function that essentially never ends, right? And that tells us that, hey, we as humans, we made an error in our code. And what's the error? Well, the error is just like it did the first part of exactly what we wanted it to do, except we never told it when to stop. And so this brings up the first kind of key principle of recursion, is that whenever you have a recursive function, you always want to be very clear about what your base case is. What's the base case? The base case is basically when your recursion stops, when your function stops running. Okay, and so in our case, if I only want to count down from 5 all the way till 1, Well, when num becomes less than 1, I stop. Right? In this case, I have an if statement that just says, if num is less than 1, I console log out done. And then if num is not less than 1, well, now we keep our code from the previous time where we console log out num, and then we call countdown with num minus 1. And so now if I call countdown 3 again, let's take a look at how it looks on our call stack. The first step is I call countdown 3. It's going to take me to line 1, then line 2, then line 3. And I'm going to say, is num less than 1? And the answer is no, it's not. It's 3, right? 3 is greater than 1. So then we jump to our else clause. We console log out 3, and then we call countdown of 3 minus 1, which is 2.
Do you need an else here? Or would it assume it's else if that top part is not true?
You want the else because you want the computer to only do one of two things. You want it to either console log out done, or you want it to recursively call a function. If you don't have the else there, if the number is less than 0, it will both console log out done, and then it will keep recursively calling itself. Right. So in this case, the else is necessary. Anywho, yeah. So our last step to finishing countdown 3 is to finish countdown 2. So then we go through this whole function again, right? Except now num is 2. And we say if num is less than 1, no, it's not. It's 2. It's greater than 1. So we go to our else clause. We console log out num, which is 2, and we call countdown of 2 minus 1, which is countdown 1. We go through our loop one more time. If num is less than 1, it's not. It's equal to 1. So then we go to our else clause. We console log out 1, and then we call countdown of 1 minus 1, which is 0. I'm now calling countdown 0, right? And at this point, I go to my if clause and say, is num less than 1? And the answer is, yeah, it is. So then I console log out done. I skip my else clause, right? Because I already triggered my if clause. And at this point, what's happening? Well, I finished countdown 0. Right? Because when num is 0, all my function does is it hits the if clause, it console logs out done, and I'm done with the function. And so now I can take countdown 0 off my call stack. I can pick up where I left off. Well, where did I leave off? I left off trying to finish countdown 0 so I can finish my countdown 1 invocation. And so now that I've finished countdown of 0, what else do I have to do in my countdown 1 invocation? And the answer is nothing. Right? I've now finished invoking countdown 1 as well. Why did I invoke countdown 1? It was because I needed to finish countdown 2. So now countdown 2 is finished, and then therefore that leads to countdown 3 being finished. And now I've finished up invoking every line of code on this page. And if you look at my printouts, I happen to have printed out 3, 2, 1, done. Okay. And so this is pretty much like the most basic core kind of example of how recursion works is I have a function. All it does is it does one thing, right? It's going to print out the number that I want to print out. It stops doing that once the number becomes less than 1. So that's my base case. But if my base case isn't triggered, then all it does is it prints out the number, and then it also it keeps calling itself. But this time, rather than keep calling itself with the same number, it calls the number by itself minus 1. So hopefully the idea is that at some point we get to the end of the function. Sorry, we get to the end of this end of this recursive process. Does this make sense so far?
Yeah.
Yeah. So once again, we always need to define a base case, and then your recursive case. You want it to keep calling the function, but eventually you want that call to hit the base case, right? And so usually what that means is you're modifying one of the inputs to the base case, or sorry, you're modifying one of the inputs to the recursive function in some way that gets you closer and closer to hitting the base case scenario. Recursion becomes a lot more complicated. We have to return a value, but once again, the same kind of principles apply, right? Step 1 is define base case, and step 2 is make sure we get closer and closer to the final output. So let's take a look at another example. Here we're doing a function that basically takes a number and returns the factorial of that number. And just as a reminder, factorial means the product. So if I multiply all the numbers between 1 and a number together, what do I get? Right. So if I'm trying to find factorial of 5, that's just 5 times 4 times 3 times 2 times 1. Okay, so that's all I'm trying to do is find the factorial. Yep. And so if we take a look at the way we would build out this function here, the base case then becomes, okay, well, when do we stop multiplying? Here this says the base case is num 0 or 1. We can probably just use 1. It's the same idea, right? Well, if the number is 0 or 1, then we just return 1, right? Because the factorial of 0 is 1, and the factorial of 1 is 1, right? There's no math there. That's just like a straight, like, this is the answer. And so this is kind of our base case scenario, and we can test it out. Factorial 0 gives me 1. Factorial 1 gives me 1, okay? So this is our base case because once num becomes 0 or 1, we basically stop the function. Well, then it begs the question, what happens when num is not? When num is not 0 or 1? And for now, we'll just assume that we're only going to do factorial of positive numbers. Okay. So if I go back and look at the pattern that we were talking about earlier, right? Factorial 0 and 1 are both 1. That's just what it is. But when I look at factorial 2, that's 2 times 1, or in some cases, the factorial of 1. If I look at 3, that's just 3 times 2 times 1. But I've already established that 2 times 1 is a factorial 2. And so 3 factorial is just 3 times a factorial 2. If I go to 4, that's 4 times 3 times 2 times 1. But I've already established that 3 times 2 times 1 is just a factorial 3. And so the factorial of 4 becomes 4 multiplied by the factorial of 3, and so on and so forth. And we kind of see this pattern start to emerge. So if I actually wanted to codify this in code, how it will look is I keep my base case from before, right? Because once again, if num is 0 or 1, I know I can stop. But in my recursive case, is what I do when I keep going? Well, and ignore this for now. In my recursive case, what I want to do is, if the number is 2, well, then I know that if I know that num is equal to 2, if you read line 8 there, the question that we want to kind of answer is, what do we get if we call factorial again with num of n minus 1? Because if I'm trying to find the factorial of 2, I know that's just 2 multiplied by the factorial of a number 1 less than it, right? Which in this case is factorial of 1. And so if I keep pushing that train of thought down more and more, then I get to line 8, which is just saying, hey, let's just print out the number multiplied by the factorial of that number minus 1, right? So if I try to do factorial of 5, for example, that just takes me to console log on line 8. It would just become 5 multiplied by the factorial of 5 minus 1, which is just 4, right? So it becomes 5 multiplied by the factorial of 4. So if we actually do this in terms of writing the final code, we kind of see how it looks in practice, right? Here, this is kind of the final version of the result in terms of kind of how we want to string out this logic here. If I take a look at line 12, I'm trying to find what the factorial of 2 is, right? So if I call factorial of 2, as I run through the first iteration of it, I check on lines 3 through 5, is num 0 or 1? No, it's not, it's 2. So then I skip all that. On line 8, I say, okay, great. Factorial of 2 is just equal to 2 multiplied by the factorial of 2 minus 1, so factorial of 1. So that requires me to now call factorial 1. Well, what's factorial 1? Factorial 1 is just 1. So I can return a 1, and then I return it back to line 8, and I say, great, that means result is just 2 times factorial 1, which is just 1. So then, therefore, result is just 2, and then I can return my result, and at that point, I figure out the answer. If I want to do the same with factorial of 5, then it's the same exact process, right? On my first iteration, as I go through it, num is equal to 5, and so I skip lines 3 through 5. I get to line 7, and it's telling me, hey, result is equal to 5 multiplied by the factorial of 5 minus 1, which is factorial of 4. Well, before I move further in my code, I now need to figure out what factorial of 4 is, right? Well, what's factorial of 4? Factorial of 4 is just equal to, if I go through this function again, I skip lines 3 through 5 because num is not 0 or 1, it's 4. I get to line 7 again, and it tells me that factorial of 4 is just 4 multiplied by factorial of 4 minus 1.
But it's going to be infinite again. Oh, never mind. When it's 0, it's going to return 1. Okay.
Yep. And so factorial of 3, and so then I go to same factorial of 3 equals 3 times factorial of 2. 2 equals 2 times factorial of 1. And what's factorial of 1? Well, factorial of 1, I hit my if clause, right? My if clause gets triggered. It just returns a 1. And remember, once a function hits a return statement, the function ends right then and there. So once I return a 1, at that point, I'm just done, right? So factorial 1 is just 1. So now if you keep right on the bottom right hand corner of the screen as we look through our table now, because factorial 1 returned a 1, I can just plug that into previously where I was calling factorial 1, and now factorial 2 becomes just 2 times 1, which is just 2. And now I can go to my previous function call where I was trying to figure out what factorial 2 was, and now I can replace just 2, and I can multiply by 3 equals 6. And then I go back, factorial 3 becomes 6, so then factorial 4 becomes 4 times 6, which is 24. And then finally, factorial 4 becomes 24, factorial 5 becomes 5 times 24, which gives me 120. And now, yep.
Sorry, yeah.
Go ahead.
Oh, I was just going to see if I understand it correctly. Num is 5, so result will equal 5 times 4. So now result is... result is 5 times factorial 4, so it's forcing, so you're multiplying by the function.
Yep.
By the result of the... Oh, Jesus. I get it, but it's just, it's hard for me to wrap my mind around it.
Yeah, and definitely. And so these slides are available to you on the platform. This slide especially, I would be the one that I would kind of focus on. Make sure you understand how we get to here. I know that it's hard sometimes for your brain to process it if you're looking at it live, so definitely take some time after the lecture to take a look at it kind of in more depth and give yourself some time to think through it. But essentially what we're doing here is just saying, in order for me to get factorial 5, it's just 5 multiplied by factorial 4. So then from here on out, all I'm trying to do is figure out what factorial 4 is. And factorial 4 is telling me, hey, I'm just 4 multiplied by factorial 3. So then I need to figure out what factorial 3 is. And that cycle goes on and on until I hit factorial 1, at what point I just say, okay, great, factorial 1 is just 1. Once I know what that is, right, then I can kind of go back over and over and over and over again and kind of unwrap myself. If I use a real-world analogy, it's like you asking, it's like, let's say you're in the military, right, and let's say you're the lowest rank. Someone says, what do I do? You would say, well, I need to ask, or if you're a company, right, you ask, someone says, hey, what should you do? You say, well, let me ask my manager what to do. And then your manager asks his manager, and his manager asks his manager, and so on and so forth, right? Let's say you get all the way up to your CEO. And your CEO says, do this. Well, then the person who asked the CEO now tells the person who asked him what the CEO said. And then that person tells the person who asked him what the CEO said. And so it's almost like you create this chain where you keep passing, where you make a longer and longer request for information. And then once you get it, that same information is kind of passed back down the chain. And so that's all we're doing here, right? Is all the work we're doing here is to figure out what factorial 5 is. And the only reason why we need to do factorial 4 is because we need to know what factorial 4 is in order to figure out what factorial 5 is. And so as we go through the sequence, we plug in the result from our previous ask all the way until we get to the very end, and we get to factorial 5 gives us 120. So yeah, the takeaways are, once again, very simple. Write your base case first and test it. And just make sure that as you write these code more and more, that you're making sure that you're covering your edge cases. And so this usually means that before you write even a function, you should have some sense of the kind of data you're going to be using on it and how you want to verify that you've written it correctly. Yep. So recursion you can use on any type of iterable data in JavaScript. So usually that just basically means arrays and strings. We just give you a few other examples, like sum array, for example, is a way for us to add up all the numbers in an array. And on line 14 there, if we do have a lot of nested arrays, that becomes a situation in which recursion becomes extremely powerful, and we'll walk through that example in more depth on Monday. Yep. That's pretty much it. So I know you probably have some confusion, some questions. I think at this point, if you have any questions, definitely ask right now. But you also want to take some time to kind of think through it and look over the slides. Like, that's also extremely okay.
If the course is over and I'm solving my learned problems, am I still able to contact people there for help?
I mean, just like you have access to the channel,